Good morning, all. I am R.M. Uma, Assistant Professor of EEE Department in Sri Muthukumaran Institute of Technology. In the subject Basic Electrical and Electronic Circuits, we are going to study Kirchhoff's law, which are fundamental rules used to analyze electrical circuits. These two laws are given by Gustav Robert Kirchhoff. Is a German scientist which are very useful in writing network equations. These laws are known as Kirchhoff's current law and Kirchhoff's voltage law, which is nothing but KCL and KVL. The first law deals with flow of current and it is popularly known as Kirchhoff's current law, while the second one deals with voltage drop in a closed circuit and is known as Kirchhoff's voltage law. Let's see on Kirchhoff's current law, which is KCL. This law states that the algebraic sum of current meeting at a junction or a node in a circuit is 0. Or this can also say the sum of current flowing towards a junction or a node is equal to the sum of current flowing outside of the junction. The current entering the junction has been taken as positive, while current leaving the junction has been taken as negative. Let us have this figure. To a junction, there are 6 branches of current entering and leaving the junction. According to Kirchhoff's current law, the sum of current leaving is equal to the sum of current entering. So as per the law, the equation we have, which is I1 plus I2 plus I6 is equal to I5 plus I3 plus I2. Here I1, I6, I4 are entering to the junction, whereas I5 and I3 and I2 are leaving the junction. Next, the Kirchhoff's voltage law. KVL states that any instant of time, the algebraic sum of voltage in a closed loop is 0. That is, the sum of the EMF raised in voltage around any closed loop of a circuit equals to the sum of potential drop in that loop. In any network, the algebraic sum of voltage drop across the circuit elements of any closed path is equal to the algebraic sum of EMF in the path. The rise in potential can be assumed to be positive, while fall in potential can be considered to be negative. So that as shown in these figures, in a source voltage, positive to negative as in fall in voltage. Similarly, negative to positive rise in voltage. The same thing as shown across the resistors, the fall in voltage is positive to negative, and similarly the rise in voltage. Now let's see on series and parallel circuits. Resistance, capacitance and inductance are often connected in series and in parallel or a combinations of series and parallel. We need to calculate the division of voltage and current in such circuits. Let's first see on series circuit. When a number of resistors are connected end to end across a source of supply, there will be only one path for the current to flow as shown in the figure. The circuit is called a series circuit. This is the series circuit where R1, R2, R3, R4 are connected in series. End to end across the source is connected. So the current flowing across all the resistors will be same. So we know I is nothing but the current which flows throughout the circuit will be same. The equivalent current is nothing but I into R1 plus I into R2 plus I into R3 plus I into R since V is equal to I into R. The equivalent circuit is nothing but R1 plus R2 plus R3 plus R4. So the equivalent circuit here it is shown, which is nothing but R1, R2, R3, R4, and the current will be same across all the resistors as the circuit is connected as in series. Next, parallel circuit. When the number of resistors are connected in such a way that both the ends of individual resistors are connected together and two terminals are brought out for connection to another part of a circuit, then the resistors are called connected in parallel as shown in this figure. The voltage V is connected across three resistors R1, R2, R3 are connected in parallel. The total current drawn from a battery is I. The current gets divided into I1, I2, I3 such that I is equal to I1 plus I2 plus I3. As the voltage V is appearing across each of these three resistors, so we can write the equation that is nothing but I is equal to I1 plus I2 plus I3, where I1 is equal to V by R1, similarly I2 is V by R2, similarly R3 is V by R3. So these three resistors are connected in parallel, where the total current I is nothing but I1 plus I2 plus I3. The equivalent circuit of this parallel circuit are shown in this figure. Next, series parallel circuit. The figure shows the number of resistors connected in series and parallel combination. Here, two parallel branches of one resistor all connected in series are shown in figure. To determine the equivalent resistance across the end terminals of the entire circuit, we first calculate the equivalent resistance of parallel branches, then put them in series along with any individual resistance already connected in series. So as by the statement here, the R1, R2 are connected in parallel, which has been calculated by R1, R2 by R1 plus R2. And similarly, this is nothing but the equivalent resistance of R1, R2. And similarly, R4 and R5 are connected in parallel. So first these to be reduced, and similarly R4 and R5 to be reduced, then these connected in series as shown here, RAB, R3 plus RCD. Or otherwise this is nothing but these two branches, and these two nodes are mentioned here. So the total resistance of a given circuit which is connected in series and parallel will be calculated in this way, as this R1, R2 are in parallel with R3, and similarly R4 and R5 are parallel in series with R3. This is a way the total equivalent circuit of a given circuit which is calculated for a series parallel circuit. So all these as taken from the reference book as shown here. Thank you all. Have a wonderful day.